Hey everyone, welcome to a deep dive into the world of large language models. You know, the AI behind things like ChatGPT. Ever wondered how these things actually learn? Like, how does code go from spitting out gibberish to composing poems or explaining quantum physics?
Yeah, it really is remarkable.
We've got some fascinating sources for this deep dive.
Okay.
A technical Medium article on fine-tuning LLMs with Kulorara.
hmm
Another one breaking down the architecture of LLMs and transformers.
Okay.
Some actual lecture notes on training and applying language models.
Yeah.
And to top it off, a DataCamp article about the hottest generative AI interview questions.
Wow.
Seems like this stuff is important for landing a job these days.
Yeah, definitely.
So our mission today, we're not just using LLMs, we're understanding how they're built. It's like peeking under the hood of a supercar and seeing the engine that makes all the magic happen.
It is fascinating how we've gone from simple chatbots to AI that can write code and generate realistic images.
Right.
But at their core, LLMs are all about language. They're sophisticated algorithms trained on mountains of text data.
And that data is key.
Okay.
We're talking books, websites, social media posts, anything that can teach an LLM the nuances of human language.
It's like building a giant digital library for the LLM to study.
Exactly.
But how do they actually make sense of all that information?
Okay.
It's not like they're just memorizing every word.
This is where the real magic happens. The architecture of LLMs.
Okay.
They use something called a transformer model, which is a specific type of neural network designed to understand the relationships between words in a sentence.
Okay.
It's not just about recognizing individual words.
Right.
It's about understanding grammar context and how words work together to convey meaning.
So it's about seeing the big picture, not just the individual puzzle pieces. But how does that actually work? What makes transformers so special?
One key feature is something called the attention mechanism.
Okay.
Think of it like a search engine for words.
Okay.
Let's say the LLM encounters a word it needs to understand better. That's the query, like when you type something into Google. Right.
The attention mechanism scans the surrounding words, those are the keys,
Okay.
and finds the ones most relevant to the query. Then it pulls the meaning or value from those relevant words to help the LLM understand the query word in context.
So it's like the LLM is cross-referencing the words in a sentence to build a deeper understanding, kind of like we do when we read.
Precisely.
Wow.
And this attention mechanism is crucial for how LLMs generate text. They use a technique called autoregressive text generation, which means they build text piece by piece, predicting the next word based on what came before.
Okay.
This is how they can write coherent paragraphs, compose poems, or even generate code.
That's pretty incredible.
Yeah.
So it's not just about memorizing words, it's about understanding the patterns and relationships between them.
Exactly.
But we keep hearing these names like GPT-3, LaMeP2, Gemini. Are those examples of LLMs?
Absolutely. Those are some of the stars of the LLM world. Each one is built using these principles we've been discussing: massive data sets, transformer architecture, attention mechanisms.
And as we delve deeper into how these LLMs are actually constructed, you'll start to see what makes them so powerful and what sets them apart.
Okay, I'm ready to go deeper. Let's talk about how you actually build one of these LLM brains.
Oh.
What are the ingredients and how do you put them all together?
Building an LLM is a multi-stage process. And the first step is gathering that massive amount of text data we talked about.
Right.
This data is the foundation of the LLM's knowledge, its training ground.
Yeah.
And the more data you have, the better.
So it's like building a giant, messy library for the LLM to explore.
Yeah.
But I imagine you can't just dump all that raw data into the LLM and expect it to learn.
You're exactly right.
Okay.
Think of it like preparing ingredients before you cook.
Right.
That data needs to be cleaned and prepped. You have to remove duplicates, fix errors, and format it in a way that the LLM can understand.
Okay.
It's a crucial step that often gets overlooked, but it's essential for training an effective LLM.
So beta is the first ingredient. What's next? Once you have your prepped data, you need to design the architecture of the LLM.
Okay.
We know it'll be based on transformers,
Right.
but there are different types of transformer architectures like encoder, decoder, causal decoder, and prefix decoder, each with its own strengths and weaknesses.
So different architectures for different LLM talents.
Yeah.
That's pretty interesting. Does the choice of architecture depend on what you want the LLM to do?
Absolutely. If you want an LLM that excels at translation, you might choose an encoder-decoder model.
Okay.
If you want one that's great at generating creative text formats like stories or poems, a decoder-only model might be a better fit.
Gotcha.
The choice of architecture is a key decision in the LLM building process.
Okay, so we've got the data, the architecture. What happens next? How do you actually make this thing learn?
Now comes the really heavy lifting. Training the LLM.
Okay.
This is where you feed all that prep data into the LLM and let it learn the patterns and relationships between words.
Right.
This process requires incredibly powerful computers, often specialized hardware designed for handling the massive scale of data and complex calculations involved.
So it's like giving the LLM's brain a super intense workout, pushing it to learn and adapt.
Exactly.
But I imagine the bigger the LLM, the more intense these workouts need to be.
You're exactly right. The scale of training is crucial. More data, more parameters, which are like the connections between neurons in the LLM's brain, and more compute power equals a more capable LLM.
Okay.
It's building a more complex brain for the AI.
Wow.
And this is where things like fine-tuning and techniques like QLARA come in, but we'll delve into those a bit later.
Okay, so we've got a glimpse of the LLM construction process. But I'm curious about the different types of transformer architectures you mentioned.
Yeah.
Can we dive a bit deeper into those? I want to understand what makes each one unique and what they're good at.
Of course. Let's start with perhaps the most well-known architecture, the decoder-only model. This is the type used in some of the most popular LLMs, like the GPT series. As the name suggests, it focuses primarily on the decoder part of the transformer.
And remind me again, what does the decoder do?
Think of the decoder as the writer of the LLM.
Okay.
It takes the information processed by the model and uses it to generate new text word by word.
Okay.
In a decoder-only model, there's no separate encoder to analyze the input text.
So how does it figure out what to write if there's no encoder giving it instructions?
That's the fascinating part.
Okay.
Decoder-only models are trained on massive amounts of text data, and they learn to predict the next word based solely on the patterns they've observed in that data. It's like learning a language by listening to a lot of conversations. You start to pick up on the patterns and can predict what someone might say next.
So it's all about statistical relationships between words.
Yeah.
It's pretty amazing. But if there's no encoder to guide it, what are decoder-only models good at?
They excel at tasks where the focus is on creative text generation.
Okay.
Think writing stories, poems, even code. They're free to generate text without being constrained by a specific input, which allows their creativity to really shine.
So it's like the decoder has been set free to be imaginative. That makes sense.
Exactly.
But what about those other architectures, like encoder-decoder models?
Right.
How do they work?
Encoder-decoder models are a bit different. They have both an encoder and a decoder, which work together to process and generate text.
Right.
The encoder's job is to read and understand the input text, while the decoder, as we've discussed, generates the output text.
So they have separate teams for reading and writing, working together to produce the final product.
A good analogy. This type of architecture is particularly well suited for tasks where understanding the entire input is crucial.
Okay.
Things like translation or summarization, where you need to capture the full meaning of the input before generating an accurate output.
It sounds like each type of architecture has its own strengths and weaknesses, depending on the task at hand.
Right.
This is also fascinating, but can we dig a little deeper into how these different architectures actually manage to predict the next word? That seems like a pretty complex calculation.
It is complex, but it all boils down to probability.
Okay.
Whether it's a decoder-only model relying on patterns or an decoder model using context from the encoder, the LLM assigns a probability to each word in its vocabulary.
Okay.
The word with the highest probability becomes the most likely candidate for the next word in the sequence.
Okay.
And this process repeats word by word until the entire output is generated.
So it's like the LLM is constantly weighing the odds, deciding which word is most likely to come next based on what it's learned from the data. But how does it learn to assign these probabilities in the first place?
That's where the training process comes in. Remember those massive data sets we talked about? During training, the LLM is fed all that data and learns to predict the next word based on the surrounding context. The more data it sees, the better it gets at accurately predicting the next word.
It's all about practice.
It's just like a human learning a language.
Exactly.
But before we move on, can you remind me how this attention mechanism we discussed earlier fits into all this?
Of course. The attention mechanism is what allows the LLM to focus on the most relevant parts of the input when predicting the next word. It's like having a spotlight that highlights the most important information.
So instead of treating every word in the sentence equally, the LLM can zero in on the words that really matter.
Exactly. It's like reading a news article and paying close attention to the key facts while skimming over the less important details.
Okay.
The attention mechanism allows the LLM to do the same thing with text, dynamically shifting its focus as it processes information.
This is all starting to make sense. It's remarkable how these LLMs can mimic the way humans read and understand language.
It truly is.
Yeah.
And it's a testament to the ingenuity of the researchers who developed these models.
Right.
They've created systems that can learn to process and generate language at a level we never thought possible before. This has been an incredible journey so far. We've covered a lot of ground, from the basics of LLMs to the inner workings of their transformer architectures. But I'm already feeling like my brain is at capacity.
Yeah.
Maybe it's time for a quick recap of what we've learned.
A great idea. We started by defining what LLMs are, these sophisticated algorithms trained on vast amounts of text data.
Right.
We then dove deep into their transformer architecture, exploring the decoder, and that crucial attention mechanism that allows them to understand and generate text like never before.
And we even touched on the different types of transformer architectures, like decoder-only models and encoder-decoder models, each with its own strengths and weaknesses depending on the task.
Right.
But before we wrap up this part of our deep dive, I'm curious to know more about the training process. You mentioned it requires incredibly powerful computers. How does that work?
Training an LLM is a computationally intensive process, often requiring specialized hardware like GPUs or graphics processing units, which are designed for the parallel processing needed to train these massive models efficiently.
So it's not something you can just do on your average laptop.
Right.
But I'm curious about the details.
Okay.
How do you actually feed all that data into the LLM, and what happens during the training process?
Well, imagine you have this vast digital library filled with text data. During training, we feed this data into the LLM piece by piece.
Oh.
The LLM's task is to predict the next word in a sequence based on the words that came before.
So like a giant game of guess the next word?
Exactly, but at a much more sophisticated level.
Right.
Initially, the LLM's guesses will be pretty random,
Sure.
but with each prediction, it receives feedback on whether it was right or wrong.
Okay.
Based on that feedback, it adjusts the weights of the connections between its artificial neurons, which are like those parameters we talked about earlier.
So it's like the LLM is learning from its mistakes, getting better with practice.
Precisely. And this process repeats even billions of times.
Wow.
As the LLM churns through the massive data set.
Okay.
Over time, it gets incredibly good at predicting the next word, capturing the nuances of language grammar and style.
That's pretty mind-blowing.
Yeah.
But all this training must take a lot of time and computational power.
Yeah.
How long are we talking, and what kind of hardware do you need?
You're right. Training an LLM is a resource-intensive process.
Okay.
It can take days, weeks, or even months, depending on the size of the model and the data set.
Wow.
And you need specialized hardware like those GPUs we mentioned earlier.
Right.
These GPUs are designed for the kind of parallel processing that's essential for handling the massive calculations involved in training.
So it's not something you can do on your average desktop computer.
Right.
But let's say you've trained your LLM.
Okay.
What happens next? How do you actually use it?
Well, once the LLM is trained, you can use it for various tasks, depending on its architecture and training data.
Okay.
One common application is text generation. You provide the LLM with a prompt, a few words, a sentence, or even just a topic, and it generates text that continues from that point.
So it's like the autocomplete feature on your phone,
Yeah,
but on a much grander scale.
that's a good analogy. But instead of suggesting just a few words, the LLM can generate entire paragraphs, stories, or even articles.
Wow.
And because it's learned those statistical relationships between words, the generated text is often surprisingly coherent and engaging.
That's pretty incredible. But what about those other architectures we discussed, like encoder-decoder models?
Right.
Are they used for different types of tasks?
Absolutely. Encoder-decoder models are particularly well suited for tasks like machine translation.
Okay.
The encoder analyzes the input text in one language, capturing its meaning, and then the decoder uses that information to generate the equivalent text in another language.
So it's like having a separate team for understanding and translating, working together to produce an accurate and fluent translation.
Exactly. And beyond translation, LLMs are being used for a wide range of tasks, from writing different kinds of creative content to summarizing long documents, answering questions, even generating computer code.
It's like having a superpowered language assistant at your fingertips.
Yeah.
But we've also been talking a lot about fine-tuning. Can you remind me how that works and why it's important?
Sure. Fine-tuning is the process of taking a pre-trained LLM and further training it on a more specific data set or for a particular task.
Huh.
Think of it like taking a brilliant student and giving them specialized training to become a doctor or a lawyer.
So you're essentially tailoring the LLM's knowledge and skills to a specific area of expertise.
Precisely. For example, you could fine-tune an LLM on a data set of medical textbooks and research papers to make it an expert in medical diagnosis.
Okay.
Or you could fine-tune it on legal documents to make it a whiz at legal analysis.
It sounds like fine-tuning can unlock even more potential from these LLMs.
Yeah.
But doesn't that require a lot of additional data and computational resources?
It can, but that's where techniques like parameter-efficient fine-tuning or PEFT come in.
Okay.
PEFT methods aim to make fine-tuning more efficient by reducing the number of parameters that need to be updated during training.
So it's like finding shortcuts to make the fine-tuning process faster and less resource-intensive.
Exactly. One popular PEFT technique is called low-rank adaptation, or LOA.
Okay.
LOA works by freezing the pre-trained weights of the LLM and introducing small trainable adapter modules into the model's architecture.
So instead of updating all those billions of parameters, you just focus on these smaller adapter modules.
Precisely. These adapter modules learn the task-specific knowledge without altering the pre-trained weights.
Okay.
This makes fine-tuning much faster and requires less computational power, making it more accessible to those who don't have access to massive computing resources.
That's incredible. It's like opening up a world of possibilities for customizing LLMs and making them even more useful.
It really is. Fine-tuning techniques like LoRi are making LLMs more adaptable and versatile, paving the way for even more innovative applications in the future.
This has been a fascinating deep dive into the world of LLMs. We've gone from the basics of their architecture to the complexities of training and fine-tuning.
Yeah.
But before we wrap up,
Okay.
I'm curious to know more about the future of this technology.
Mm-hmm.
What are some of the emerging trends and advancements we should be keeping an eye on?
That's a great question. The field of LLMs is rapidly evolving, and there are some truly exciting developments on the horizon. One trend we're seeing is the move towards multimodal LLMs,
Okay.
which can process and generate not just text, but also images, audio, and even video.
So we could have an LLM that can write a story and then generate the accompanying illustrations and soundtrack.
Exactly. Or an LLM that can understand both your spoken commands and the images you show it, responding in a way that integrates both types of input. The possibilities are truly mind-blowing.
That's amazing. What other advancements are researchers working on?
Well, there's a lot of focus on improving the reasoning abilities of LLMs, making them better at solving complex problems and making logical inferences.
Okay.
Imagine an LLM that can not only write a legal brief, but also analyze a case and predict the outcome of a trial.
So they could go beyond just pattern recognition and actually think for themselves. That's pretty incredible.
It's a challenging area of research, but the progress being made is really exciting. And of course, there's ongoing work to make LLMs more efficient and accessible.
Yeah.
We're seeing a push towards smaller, more specialized LLMs that can run on less powerful hardware, which could bring the power of this technology to a much wider audience.
So we might see LLMs running on our smartphones or even embedded into everyday objects. The possibilities seem endless.
They really do. The field of LLMs is still relatively young, but it's clear that this technology has the potential to revolutionize countless industries and aspects of our lives.
This has been a truly enlightening journey.
Yeah.
I feel like I've gained a much deeper understanding of not just what LLMs are, but also their potential impact on the world.
It's been my pleasure to share this journey with you, and I hope our listeners have found it informative and inspiring as well.
I'm sure they have. But before we wrap up, there's one more thing I'm curious about. You've talked about all these amazing applications of LLMs, but what about the potential downsides? Are there any risks or ethical considerations we should be thinking about as this technology continues to advance?
That's an important question and one that researchers and developers are grappling with as we speak. One of the key challenges is ensuring that LLMs are used responsibly and ethically.
You mentioned ensuring LLMs are used responsibly and ethically. What are some of the concerns in that area?
One of the biggest challenges is bias. Because LLMs are trained on massive data sets of human-generated text, they can inadvertently learn and reproduce the biases present in that data.
So if the training data contains biased language or stereotypes, the LLM might end up generating text that reflects those biases.
Exactly. This could lead to outputs that are discriminatory, offensive, or even harmful. It's a serious concern, and researchers are actively working on ways to mitigate bias in LLM training and outputs.
It sounds like a tricky problem to solve. What other ethical considerations are there?
Another concern is the potential for misuse. LLMs can generate incredibly realistic and convincing text, which could be used to spread misinformation, create fake news articles, or even impersonate real people.
It's like the deep fakes of the text world.
That's a good analogy. It's crucial to develop safeguards and promote responsible use to prevent these kinds of malicious applications.
These are definitely important things to consider as this technology continues to advance. But let's shift gears a bit and talk about the more positive applications. We've touched on some of them already, but can you give me some specific examples of how LLMs are being used in the real world today?
Absolutely. One area where LLMs are already making a big impact is in customer service. Many companies are now using LLM-powered chatbots to handle customer queries, provide support, and even resolve issues.
So those frustrating phone trees might finally become a thing of the past.
Let's hope so. And beyond customer service, LLMs are being used in healthcare to analyze medical records, assist with diagnoses, and even personalize treatment plans.
Wow. So they're not just writing poems, they're potentially saving lives. What other industries are being transformed by LLMs?
Another area where LLMs are making significant inroads is education. They can be used to create personalized learning experiences, tailor educational content to individual student needs, and provide feedback on writing assignments.
It sounds like they have the potential to revolutionize the way we learn.
They certainly do. And in the realm of creative industries, LLMs are being used to write scripts, compose music, generate artwork, and even create video game content.
It's amazing to think about the creative possibilities these LLMs are unlocking. It feels like we're just scratching the surface of what this technology can do.
I agree. And as LLMs continue to evolve, we can expect to see even more innovative and impactful applications emerge across all sectors of society.
This deep dive has been truly eye-opening. We've explored the inner workings of LLMs, from their transformer architectures to the complexities of training and fine-tuning. We've discussed their potential benefits and the ethical considerations we need to keep in mind. It's been an incredible journey.
It's been a pleasure sharing this exploration with you.
And for our listeners, if you're eager to learn even more about this fascinating world of LLMs, be sure to check out the show notes for links to all the research and resources we've used in this deep dive. Until next time, keep those brains buzzing.